So let's talk about something called a definite integral and using that to find the area under the curve. So far, we have not found exact areas under a curve. We're just approximating areas using Riemann sums. So we're going to go and we're going to relook at this function f of x equaling negative 1/2 x squared plus 2x over the interval from 0 to 3. So I went ahead and graphed it on my calculator. So we can see this curve here, and we want to approximate the area that's under that blue parabola. So, the first thing we would do is approximate it using we're going to use a right Riemann sum with 90 equal subintervals, and I'm going to write it using sigma notation so that way I can evaluate it on my calculator. Right, so we know that the first thing we need to know is our delta x, which is b minus a, so 3 minus 0 over the number of intervals, so in this case 9. So I get 3 over 9, which of course you could reduce to 1/3. I'm just going to leave this as an unreduced fraction though, and you're going to see why in a second. So my area approximation, if I start writing my sigma notation, right, I'm going to take the sum from 1 to 9, so my 9 subintervals, of my delta x, which is the width of my rectangles, times, and now I need to use the function to evaluate the height of each interval. So for a right subinterval, my x values that I want to evaluate my function at is going to be equal to the a value, the starting value, plus the delta x times I. So because my a value is 0, I would get 0 plus or just nothing there, and then I'm going to get 3 over 9 times I. So I'm going to go ahead and use my calculator to evaluate this. So I'm going to pull up my summation. I'm going to use the variable x here because it's easier to type on my calculator. And then times. Now, if you have an updated TI-84, the easiest way to pull up and use a stored function, you can of course use the vars key and then go over to yvars and select it. Or if you just want to stay on the home screen, if you hit alpha trace, it pulls up all of your functions there. So I want to evaluate y1 because that's where I store my calculator. My function in my calculator. And then I have 3 over 9 times my indexing variable x. Close those parentheses. So now if I wanted to make that a fraction so I can get the exact answer, I would get that Riemann sum is exactly 85 over 18. And now that number probably doesn't mean much to us if now we change it to a decimal. I get that that's about 4.722. Okay, so not a bad area approximation, right? 9 subintervals isn't bad, but what if we let the number of rectangles we use double? So right now let's use 18 subintervals. So the first thing that's going to change is our delta x, right? So this is going to become 3 minus 0 over 18, so I'm just going to leave that as 3 over 18. And then my endpoints are going to stay the same because I'm still using a right endpoint Riemann sum. So now my area is going to be the sum from 1 to 18 of my delta x, my width, of 3 over 18 times my function evaluated at 3 over 18 times I. So now you probably see why I didn't reduce that fraction, because now in my calculator, if I scroll up and copy that down, all I have to do is change all of the 9s to 18s, and I can just hit enter again. So it's way less typing. Just have to edit this formula. Work smarter, not harder, right? So now I get that this is equal to 665 over 144. And if I make that a decimal, I get that that's 4.618. So, okay, it's probably a more accurate area, right? Because we look at the number of rectangles double, which means that we are looking at probably smaller width, right? We definitely have smaller width, which means that hopefully we're fitting the curve a little bit better. So let's actually look at what that means. So if I go into Desmos, I already have the function graphed for us, and right now I have one subinterval being used for my right endpoint Riemann sums. You can see one rectangle. So the first thing when we did, we had 9 subintervals, right? So if that first one that we were doing, that 4.722 area, right, we can see that actually coming in down there. It'll calculate it for us, right? Not necessarily bad. We have some over approximation on the left where our function is increasing, and then we have some gaps under the curve on the right where it's decreasing. So now let's double it and see how it looks. Okay, so the rectangles are getting closer to that function. Seems like it's definitely a better approximation. So now the question might be, right, what does it look like if we just let it be n subintervals? We don't specify a number of subintervals. Right, so this would give us a formula for any number of subintervals that we could plug into. So now we're going to take the sum from 1 to n of 3 over n times my function evaluated at 3 over n times I. Right, so then I could plug in any value of n I want. And if we go back into Desmos here and let this kind of play out, right, I want you to pay attention to two things. What the graph is looking like as the n value increases. And if you look down here, I'm going to click in here, where my cursor is right now, you can see it's evaluating the summation. So pay attention to that I number and see what the number is doing as n increases. So I'm just going to go ahead and play. Right. So we can see as the number of n, the number of rectangles increases, right, the gap between the curve on the right, that's decreasing. That is getting much, much smaller. And then the heights on the left, right, they're getting much, much closer to the curve. Right, now we let it just keep playing, right, it's getting very, very close to the curve. Right? I have to zoom in quite a bit to see the gap on the right where it's decreasing, and over here I have to zoom in quite a lot to see the overlap on the left side. Oops. Okay, right, so at 200, we get that our area approximation is all the way down to 4.511. So now 200 is a lot, but what if I let it be 2,000? Right, if you look, Desmos at this zoom doesn't even show any rectangles, right? If I go in closer, I have to zoom in quite a bit to see that the edge of those rectangles is still happening. And my area approximation is now down to 4.501. Okay, now what if I multiply that by 10, increase this by tenfold? Oh, now I'd have to zoom in even further to see that I still have some overlap here on the left, and consequently on the right we still have a little bit of under approximation where it's decreasing. Okay, what if I just increase it tenfold again? Oh, right, so it's getting closer and closer, right? And as we look, our area approximation is now about 4.500, right? If I increase it again, right, even closer to 4.5 again, closer to 4.5 again, right? So we can probably assume that the exact area is 4.5. And as we let the number of subintervals increase, let's go back to the notes, as we let the number of subintervals increase, we're actually only looking at, right, getting smaller and smaller rectangles. So that delta x is decreasing. It's getting infinitesimally small. And so as we let the width of our rectangles get infinitesimally small like that, we're actually getting the exact area of the curve. So this is what's called a definite integral. So the definite integral definition, right, is that it incorporates a limit. So as we let the number of rectangles get bigger and bigger, so in other words, as we let n go to infinity, right? So if we take that area formula and just kind of generalize it, so we're going to let the limit of n go to infinity, so we're taking an infinite number of rectangles now, and we're taking the sum from I equaling 1 to n. That was an awful sigma, but we're going to keep it. Right? We know that the width of the rectangle is delta x, and then we want to evaluate at it some endpoint of the interval. We're just going to let that endpoint be represented by xi. So if we let n go to infinity, we say that that's a definite integral, and we symbolize that by drawing our integral symbol, but now we put limits on that, so it's going from a to b, so that's right, those are the endpoints of our area interval, and then we're evaluating f of x, and then dx, right, and that dx pops up because we are letting delta x go to infinity, right, so as n approaches infinity, right, our delta x is getting really, really tiny, so delta x becomes dx because it's infinitesimally small. Right, so just a couple of notes on the notation here. Actually, we'll just copy it down because my integral symbol is so nice up here. Right, so A and B just represent the limits of our integral. So this is the upper bound, this is the upper limit of our integral. This is the lower limit. Right, and since a definite integral is defined as the limit of a Riemann sum, right, a Riemann sum is representing the area under a curve. So the definite integral is also representing the area under a curve, and it's going to give us a numerical answer. So definite integrals give numerical answers or values as an answer. Right, definite integrals produce numerical answers. In other words, there's no plus c, right? So when we're doing indefinite integrals, we have that constant of integration. A definite integral produces a value answer, a numerical answer, so there's no plus c here, because that would just be changing the number each time. So all we're going to do to kind of wrap this up is kind of talk about that definition of a definite integral before we actually talk about how to do them without having to do the Riemann sum each time and without having to do a limiting process. You can actually evaluate a definite integral using the limit process. There's some summation formulas that you can use to help break that down and then create a function to take the limit of. That's a little bit outside the scope of this course. It would be covered in like a Calc 2 class or something, but for the sake of time, we're not covering it in here. So for our first example here, we are going to write the following definite integral as Riemann sum. I'm going to just rotate my iPad here to make this a little bigger. Okay, right, so we want to write these definite integrals as Riemann sums, and if you're taking the BC Calculus exam, this is great practice because these do pop up every once in a while and there's multiple choice questions. You want to be able to recognize the definition of this. So first thing we want to do is we want to find that delta x. So that's going to be our upper minus lower bound, so 5 minus negative 1 over n. That's going to produce 6 over n. And then my function, right, is what's inside, so that's going to be 2 times x. And then I want to evaluate it at an endpoint. So the easiest way to set these up is always to use the right Riemann sum endpoint setup. So that's always going to be your a value plus your delta x times your I. Your indexing variable. You can use whatever variable you want as the indexing variable. A lot of books use the I because that's in I indexing. A lot of places will also use K since I is often thought of as the imaginary number and they don't want to confuse the definitions. And you can see other things as well. So in this case, for this function, our a is negative 1, our delta x is 6 over n times our I. And then if we look at this here, right, so I'm going to say that this is now the limit as n goes to infinity of my summation from I going from 1 to n. Just realized I'm going to run out of room, so let's make that a little smaller off to the side. And then my delta x is going to be 6 over n times my function, which is 2x, so 2 times my xi, my endpoint. So now we could leave it like that, but if we want to simplify it, I can multiply my 6 over n times the 2 on the outside. So I'm still going to have the sum from 1 to n, but now I'm going to have 12 over n times negative 1 plus 6 over ni. So that would be the limit definition of a Riemann sum for my definite integral. And then if we want to do the same thing over here, switch colors just to make it a little easier to differentiate. Right, my delta x here, for the integral from 0 to 5 of x cubed times sine of x dx, right, I'm going to take upper minus lower, divide it by n, so I get 5 over n. My function is x cubed times sine of x. And my endpoints, using my right endpoint setup, so a plus a delta xi, it's going to give me 0 plus, so it doesn't matter. And then we're going to get 5 over n times I. So if I go and translate that into a Riemann sum, I'm going to take the limit as n goes to infinity of my sum from 1 to n of my delta x, so that's going to be 5 over n, times my function evaluated at my xi, my endpoints. So that's going to give me 5 over n times I all cubed times sine of 5 over ni. Now I could of course leave it like this, but I can also simplify these two things, multiply them together. So I can take the limit as n goes to infinity of the summation from 1 to n. So 5 over ni all cubed, so 5 cubed would be 125, and then multiply it by the 5 on the outside, I'd get 625. And then I would have n cubed coming from the inside times the n on the outside, so n to the 4th, times I cubed times the sine of 5 over ni. So that could be my final definition there. Right, and then if we can go from definite integrals to limits of Riemann sums, we can also go the other direction, going from a Riemann sum to what is the definite integral. And so once we talk about the fundamental theorem of calculus and some definite integral properties, we'll be able to evaluate these without a calculator and just like using our properties. So we have a limit. So on the outside of, if I'm looking at example C, this would be my delta x. So delta x is equal to 5 over n. And then I can see on the inside, so the inside is representing my f of xi. And what I want to pay attention to is this, right? So I can see this is my delta x here, and it's popping up over here. So this is going to be my a value. That's going to be my starting point for my interval. And I can tell that because this looks like a plus delta xi on the inside. So my a value is equal to 1. Well, if my delta x is equal to 5 over n, I know that that's equal to my upper value b minus my lower value of 1 over n. So that tells me that b has to be equal to 6. And I can see like where I'm plugging in my 1 plus delta xi, that would take place of the x in my function. So my function must be negative 2 times x to the 5th. So this right here would equal the definite integral from 1 to 6 of negative 2 times x to the 5th, and then I'm going to throw my dx in. So those are the same thing. Right? We can look at the same thing with the square root function. So again, I'm going to pull this is my delta x, right? And I can see that here as well, that this is also my delta x. Again, we have a 1 being added here, so that's my a value. So if my delta x is equal to 3 over n and my a is equal to 1, I know that this is b minus 1 over n. So b has to equal 4. And the parentheses that my a plus delta xi is housed in between, that represents where the x would be in my function. So my function here must be the square root of x minus 4. So that means that this must be equal to the definite integral from 1 to 4 of the square root of x minus 4 dx.